First, start with a piece of wood that is 8 inches wide and 5 inches tall and half an inch thick. Take a separate piece of wood and cut it into 4 pieces that are 5 inches tall, half an inch wide, and half an inch thick. Using a thin drill bit, drill 4 holes through the base and each of the corners, giving a 1/4 inch of space between the edges so that the wood does not split when you drill through it. Using the same drill bit, drill down into each of the 4 pillars, making sure the drill is in the direct center of the wood so that it doesn't split. Use a vice grip to firmly hold the pillar in place when drilling, and repeat for all 4 pillars. Next, flip the pillar, align it with the hole that is made in the base, and drill a screw upwards through the base and into the pillar. This will hold it firmly in place, and repeat for all 4 pillars. Next, take another piece of wood and cut 2 pieces that are 8 inches wide, half an inch tall, and 1/4 of an inch thick. Apply hot glue to the tops of the pillars that are 8 inches apart and firmly place the new thin piece of wood across. Repeat on the other side. Take your balls of choice and apply a dab of hot glue to it and firmly press the string in place, making sure the ball is in the center of the string when it is connected. To make the next step easier, have the string be extra long. Apply hot glue to the thin slabs of wood and hang the ball downwards into the frame, making sure that the length of each string on both sides is equal. Any excess string on each side can be cut off with scissors after the glue dries. Repeat for all 5 balls and make sure that each ball is level with each other and on the same plane. Cue the building montage.
So how does a Newton's cradle work?
It works because of a physics principle known as the conservation of energy. This states that in a closed system with no external forces, energy is always conserved. Let's look at it in action. When the ball of a Newton's cradle is raised, it is given a height h. For now, I will label it hi. The equation for the ball's gravitational potential energy is mgh, where m is the mass of the ball and g is the acceleration due to gravity near the surface of the Earth. When the ball is released, it accelerates downward and gains velocity while losing height. The equation for the ball's kinetic energy is 1/2 mv squared. So, the total amount of energy of the Earth ball system at any given point in time is mgh plus 1/2 mv squared. Because of the law of conservation of energy, E should always be a constant number. As h decreases, v squared increases, and E stays constant. At the bottom right before the collision, h equals 0. So the total amount of energy is 1/2 mv squared. This is similar to the situation where the ball is held at height hi and has no velocity. The GPE value and kinetic energy value are switched in this case. During the collision, the force of the ball travels through the other balls and accelerates the final ball upward to a height of hi. Since it reached a height of hi, and that was the initial height of the ball, all of the energy was conserved. Ideally, that is how a Newton's cradle should work, and it should go forever. But why doesn't it? Well, because energy is in fact lost. Every time a collision happens, the iconic clack sound is made between the balls. Plus, there is friction between the balls, and heat energy is generated when they collide. All of these are non-zero factors that contribute to the gradual loss of energy that Newton's cradle experiences. Misalignment is also a factor. Here, they are perfectly aligned, and the force applied from one ball to the next is perfectly horizontal. The angle of the force is 0, so the x component is 1 and the y component is 0. When they are not aligned, the force is not parallel to the ground, but instead at an angle. This causes the force to not be applied perfectly horizontal, and the y component of the force will lead to a loss of energy, because not all of the force and energy is being applied to the movement of the balls, and they won't go as high when colliding.